The Pegasus rocket was unlike any launch system before it. Designed to be released from a high-flying aircraft, it promised a revolution in how small satellites could reach orbit. Its airborne launch method offered flexibility, cost savings, and access to precise orbits. The project challenged engineers to rethink the very concept of rocketry. Developed by Orbital Sciences in the late 1970s, the Pegasus combined traditional solid-fuel rocketry with aviation technology. Each launch depended on precise timing, altitude, and speed from its carrier aircraft. Pilots and engineers had to coordinate like never before to ensure success. The story of Pegasus is one of innovation, risk, and the birth of a new era in spaceflight. The Pegasus rocket was conceived to solve a growing problem in satellite launches: cost and flexibility. Traditional ground-launched rockets were expensive and limited by weather and fixed launch sites. By releasing a rocket from a high-flying aircraft, engineers could bypass these constraints. This innovation promised a new way to reach orbit efficiently. Orbital Sciences began the design process in the mid-1970s, focusing on a three-stage solid-fuel configuration. Each stage had to be lightweight yet powerful enough to propel small payloads into orbit. Engineers carefully calculated mass ratios, thrust, and aerodynamics for stability after release. Every detail mattered. Small miscalculations could result in mission failure. The rocket was designed to be carried under the wing of a Lockheed L-1011 carrier aircraft. Modifications ensured structural integrity and safety during flight. Engineers conducted extensive simulations to test aerodynamics during high-speed drop and ignition. The integration of aircraft and rocket systems became the program's greatest engineering challenge. Attention also focused on ignition and guidance systems. The rocket needed to ignite reliably at high altitude after freefall release. Onboard computers and gyroscopes were calibrated for precise trajectory control. Engineers aimed for maximum accuracy with minimal human intervention. Safety and risk mitigation were critical considerations. The release mechanism had to function flawlessly to prevent damage to both the aircraft and rocket. Redundant systems were implemented to reduce the chance of failure. Every aspect of the design was tested extensively before even a single launch attempt. By the end of the design phase, Pegasus had taken shape on paper and in prototypes. It represented a bold departure from traditional launch methods. The combination of aircraft and rocket systems was unprecedented in the late 1970s. Engineers prepared to move from theory to the high-stakes reality of flight testing. As the Pegasus project progressed, engineers faced the challenge of integrating rocket and aircraft systems flawlessly. The L-1011 carrier aircraft required precise modifications to carry and release the rocket safely. Flight tests simulated release dynamics, aerodynamic loads, and ignition timing. Each adjustment had to be exact to avoid catastrophic failure. Engineers conducted wind tunnel tests to validate the rocket's aerodynamic stability. The three-stage solid-fuel design was refined to ensure consistent thrust and trajectory. Guidance systems were calibrated using early computer models for maximum precision. Every parameter was scrutinized before the first airborne launch attempt. The release mechanism became a focal point of development. It had to separate the rocket cleanly from the aircraft at high altitude. Engineers tested multiple locking systems and fail-safes. Any malfunction could damage both rocket and carrier, endangering the mission. Ground teams worked in coordination with pilots to perfect flight profiles. Altitude, speed, and release point were carefully calculated for each mission. Simulations included emergency scenarios to prepare for unexpected failures. The goal was to guarantee both safety and mission success. Training programs prepared pilots for the unusual responsibilities of launching a rocket in flight. Coordination between cockpit crew and engineers was critical. Each release required precise timing and exact positioning. Any deviation could compromise the launch. By the end of pre-flight preparation, Pegasus was ready for its first airborne attempt. Engineers had tested every system, from aerodynamics to ignition. The aircraft and rocket became a single, synchronized machine. The world was about to witness a revolutionary approach to space launches. The Pegasus rocket made history with its first airborne launch in 1990. Released from the modified L-1011 carrier at high altitude, it ignited flawlessly. Engineers and pilots held their breath as the rocket climbed toward orbit. The success validated years of meticulous planning and testing. Early flights tested the rocket's three-stage solid-fuel configuration. Each stage had to separate cleanly while maintaining precise trajectory. Telemetry provided real-time data on velocity, acceleration, and stability. Every successful stage separation marked a triumph of engineering precision. The aircraft-based launch method allowed unprecedented flexibility. Pegasus could reach orbital inclinations and trajectories that ground-launched rockets could not easily achieve. Engineers adjusted flight paths to maximize efficiency and payload accuracy. Each mission refined the understanding of airborne launch dynamics. Challenges persisted during initial operations. Minor instabilities and vibrations required careful monitoring and adjustments. Engineers learned to fine-tune ignition timing and release altitude. Every flight contributed vital lessons for the program's future. Payload deployment demonstrated remarkable accuracy. Small satellites reached precise orbits with minimal deviation. The combination of aircraft mobility and rocket guidance proved revolutionary. The world recognized Pegasus as a new class of space launch system. The program's success inspired confidence in commercial and military applications. Low-cost, responsive access to orbit became a tangible reality. Engineers continued to refine the rocket for heavier and more complex payloads. Pegasus was no longer a prototype. It was a functional, reliable orbital delivery system. By the end of this early testing phase, Pegasus had established its legacy. It proved that airborne launches could reduce costs and expand orbital options. Engineers and pilots had achieved what once seemed impossible. The stage was. As Pegasus entered regular service, its airborne launch system proved its unmatched versatility. The L-1011 carrier could deploy rockets from virtually anywhere, avoiding weather and ground congestion. Engineers refined release profiles for maximum efficiency and safety. Each flight demonstrated the advantages of combining aircraft and rocket systems. The rocket's reliability became a hallmark of the program. Multiple payloads reached orbit without incident, showcasing precision and repeatability. Data from telemetry allowed continuous improvement in trajectory and stage separation. Pegasus quickly gained recognition as a revolutionary method of space access. Payload capacity increased over time, enabling a wider variety of satellites to be launched. Earth observation, communications, and experimental payloads benefited from the system's flexibility. Engineers adapted guidance and control software for more complex orbital insertions. Each mission pushed the envelope of what small orbital rockets could achieve. Operational challenges remained, particularly in coordinating aircraft and ground teams. Altitude, airspeed, and release timing required flawless execution. Even minor deviations could result in significant orbital errors. Teams developed strict protocols to maintain consistency and success. The program inspired further innovation in aerospace engineering. Lessons from Pegasus influenced other air launch systems, including orbital and suborbital vehicles. Engineers applied knowledge in propulsion, guidance, and aerodynamics to new designs. Pegasus became a benchmark for combining aviation and spaceflight expertise. Public and commercial interest surged as the system proved its worth. Small satellites could now be deployed more rapidly and at lower cost than traditional launches. The flexibility of airborne launches opened new markets in research and communications. Pegasus had transformed the possibilities for orbital access. By the end of its peak operational period, Pegasus had secured its place in aerospace history. It demonstrated that innovative engineering could overcome traditional constraints. Aircraft and rocket systems working together expanded humanity's reach into space. The legacy of Pegasus continues to influence air-launched space programs today. The Pegasus rocket forever changed the way engineers thought about launching satellites. Its airborne launch system proved that flexibility and precision could coexist in orbital access. Lessons from Pegasus informed future air launch systems and small satellite deployments. The program demonstrated that innovation could solve problems traditional rockets could not. The combination of aircraft and rocket pushed aerospace engineering to new heights. Engineers mastered release dynamics, guidance precision, and stage separation in real operational conditions. Each mission provided critical data that shaped later technologies. Pegasus became a benchmark for safe and reliable air-launched orbital delivery. The L-1011 carrier aircraft played an equally vital role. Modifications and careful flight planning ensured that the rocket could be deployed safely at high altitudes. Pilots executed missions with meticulous attention to timing and coordination. The success of Pegasus relied on the perfect integration of air and space systems. Operational achievements included launching satellites for research, communications, and military applications. Each successful deployment highlighted the advantages of air launch: flexibility, reduced cost, and rapid response. Pegasus demonstrated that airborne rockets could access precise orbits with remarkable accuracy. The program's impact on the aerospace community was immediate and lasting. Technological innovations from Pegasus extended beyond the rocket itself. Advances in solid-fuel propulsion, guidance systems, and telemetry informed other spaceflight programs. Engineers applied these lessons to larger orbital vehicles and new launch concepts. Pegasus became a cornerstone in the evolution of small satellite deployment. Despite the program's age, its influence remains today. Modern air-launched vehicles, including those designed for CubeSats and responsive space missions, owe much to Pegasus. The rocket proved that unconventional approaches could succeed where traditional methods struggled. Pegasus stands as a testament to ingenuity, precision, and daring in aerospace history. Ultimately, the Pegasus rocket embodies the spirit of innovation that defines space exploration. By challenging assumptions about how rockets could reach orbit, it opened new pathways for human ingenuity. Engineers, pilots, and mission teams collaborated to turn a radical concept into reality. The legacy of Pegasus continues to inspire air-launched space programs around the world.